century, perhaps long after that, we shall either discover life beyond Earth or acquire sufficient data to conclude, as some scientists now suggest, that life on our planet represents a unique phenomenon within our Milky Way galaxy. For now, our lack of information on this subject allows us to consider an enormously broad range of possibilities. We may find life on several objects in the solar system, which would imply that life probably exists within billions of similar planetary systems in our galaxy. Or we may find that Earth alone has life within our solar system, leaving the question of life around other stars open for the time being. Or we may eventually discover that life exists nowhere around other stars, no matter how far and wide we look. In the search for life in the universe, just as in other spheres of activity, optimism feeds on positive results, while pessimistic views grow stronger from negative outcomes. The most recent information that bears upon the chances for life beyond Earth, the discovery that planets are moving in orbit around many of the Sun's neighboring stars, points toward the optimistic conclusion that life may prove relatively abundant in the Milky Way. Nevertheless, great issues remain to be resolved before this conclusion can gain a firmer footing. If, for example, planets are indeed abundant, but almost none of these planets provide the proper conditions for life, then the pessimistic view of extraterrestrial life seems likely to prove correct. Scientists who contemplate the possibilities of extraterrestrial life often invoke the Drake equation, after Frank Drake, the American astronomer who created it during the early 1960s. The Drake equation provides a useful concept rather than a rigorous statement of how the physical universe works. The equation usefully organizes our knowledge and ignorance by separating the number that we dearly seek to estimate, the number of places where intelligent life now exists in our galaxy, into a set of terms, each of which describes a necessary condition for intelligent life. These terms include the number of stars in the Milky Way that survive sufficiently long for intelligent life to evolve on planets around them, the average number of planets around each of these stars, the fraction of these planets with conditions suitable for life, the probability that life actually arises on these suitable planets, and the chance that life on such a planet evolves to produce an intelligent civilization, by which astronomers typically mean a form of life capable of communicating with ourselves. When we multiply these 5 terms, we obtain the number of planets in the Milky Way that possess an intelligent civilization at some point in their history. To make the Drake equation yield the number that we seek, the number of intelligent civilizations that exist at any representative time, such as the present, we must multiply this product by a 6th and final term. The ratio of the average lifetime of an intelligent civilization to the total lifetime of the Milky Way galaxy. Each of the Drake equation's 6 terms requires astronomical, biological, or sociological knowledge. We now have good estimates of the equation's first 2 terms, and seem likely to obtain a useful estimate of the third before long. On the other hand, terms 4 and 5, the probability that life arises on a suitable planet, and the probability that this life evolves to produce an intelligent civilization, require that we discover and examine various forms of life throughout the galaxy. For now, anyone can argue almost as well as experts can about the value of these terms. What is the probability, for example, that if a planet does have conditions suitable for life, then life will actually begin on that planet? A scientific approach to this question cries out for the study of several planets suitable for life for a few billion years to see how many do produce life. Any attempt to determine the average lifetime of a civilization in the Milky Way likewise requires several billion years of observation, once we have located a sufficiently large number of civilizations to provide a representative sample. Isn't this a hopeless task? A full solution of the Drake equation indeed lies immensely far in the future, unless we encounter other civilizations that have already solved it, perhaps using us as a data point. But the equation nevertheless provides useful insights for what it takes to estimate how many civilizations exist in our galaxy now. The 6 terms in the Drake equation all resemble one another mathematically in their effect on the total outcome. Each of them exerts a direct, multiplying effect on the equation's answer. If, for instance, you assume that 1 in 3 planets suitable for life actually produces life, but later explorations reveal that this ratio actually equals 1 in 30, you will have overestimated the number of civilizations by a factor of 10. assuming that your estimates for the other terms prove correct. Judging by what we now know, the first three terms in the Drake equation imply that billions of potential sites for life exist in the Milky Way. If you like, you can engage in soul-searching arguments with your friends, family, and colleagues about the value of the remaining three terms, and decide on numbers that will provide your own estimate for the total number of technologically proficient civilizations in our galaxy. If you believe, for example, that most planets suitable for life do produce life, and that most planets with life do evolve intelligent civilizations, you will conclude that billions of planets in the Milky Way produce an intelligent civilization at some point in their timeline. If, on the other hand, you conclude that only one suitable planet in 1,000 does produce life, and only one life-bearing planet in 1,000 evolves intelligent life, you will have only thousands, not billions, of planets with an intelligent civilization. Does this enormous range of answers, potentially even wider than the examples given here, imply that the Drake equation presents wild and unbridled speculation rather than science? Not at all. This result simply testifies to the Herculean labor that scientists, along with everyone else, face in attempting to answer an extremely complex question on the basis of highly limited knowledge. The difficulty that we face in estimating the values of the last three terms in the Drake equation highlights the treacherous step that we take whenever we make a sweeping generalization from a single example, or from none at all. We are hard-pressed, for example, to estimate the average lifetime of a civilization in the Milky Way when we do not even know how long our own will last. Must we abandon all faith in our estimates of these numbers? This would emphasize our ignorance while depriving us of the joy of speculation. If, in the absence of data or dogma, we seek to speculate conservatively, the safest course rests on the notion that we are not special. Astrophysicists call this assumption the Copernican Principle, after Nicolaus Copernicus, who, in the mid-1500s, placed the sun in the middle of our solar system, where it turned out to belong. Until then, despite a 3rd century B.C. proposal for a sun-centered universe by the Greek philosopher Aristarchus, the Earth-centered cosmos had dominated popular opinion during most of the past 2 millennia. Codified by the teachings of Aristotle and Ptolemy, and by the preachings of the Roman Catholic Church, this dogma led most Europeans to accept Earth as the center of all creation. This must have appeared both self-evident from a look at the heavens and the natural result of God's plan for the planet. Even today, enormous segments of Earth's human population, quite likely a significant majority, continue to draw this conclusion from the fact that Earth seemingly remains immobile while the sky turns around us. Although we have no guarantee that the Copernican Principle can guide us correctly in all scientific investigations, it provides a useful counterweight to our natural tendency to think of ourselves as special. Even more significant is that the principle has an excellent track record so far, leaving us humbled at every turn. Earth does not occupy the center of the solar system, nor does the solar system occupy the center of the Milky Way galaxy, nor the Milky Way galaxy the center of the universe. And in case you believe that the edge is a special place, we are not at the edge of anything either. A wise contemporary attitude therefore assumes that life on Earth likewise follows the Copernican Principle. If so, how can life on Earth, its origins, and its components and structure provide clues about life elsewhere in the universe? In attempting to answer this question, we must digest an enormous array of biological information. For every cosmic data point, gleaned by long observations of objects at enormous distances from us, we know thousands of biological facts. The diversity of life leaves us all, but especially biologists, awestruck on a daily basis. On this single planet Earth, there coexist algae, beetles, sponges, jellyfish, snakes, condors, and giant sequoias. Imagine these 7 living organisms lined up next to each other in order of size. If you didn't know better, you would be challenged to believe that they all came from the same universe, much less the same planet. Try describing a snake to somebody who has never seen one, you gotta believe me. I just saw this animal on planet Earth that stalks its prey with infrared detectors, swallows whole live animals up to 5 times bigger than its head, has no arms or legs or any other appendage, yet can slide along level ground almost as fast as you can walk. In contrast to the amazing variety of life on Earth, the constricted vision and creativity of Hollywood writers who imagine other forms of life is shameful. Of course, the writers probably blame a public that favors familiar spooks and invaders over truly alien ones. But with a few notable exceptions, such as the life forms in The Blob and in Stanley Kubrick's 2001, A Space Odyssey, Hollywood aliens all look remarkably humanoid. No matter how ugly they may be, nearly all of them have 2 eyes, a nose, a mouth, 2 ears, a head, a neck, shoulders, arms, hands, fingers, a torso, 2 legs, 2 feet, and they can walk. From an anatomical view, these creatures are practically indistinguishable from humans, yet they are supposed to live on other planets, the products of independent lines of evolution. A clearer violation of the Copernican Principle can hardly be found. Astrobiology, the study of the possibilities for extraterrestrial life, ranks among the most speculative of sciences, but astrobiologists can already assert with confidence that life elsewhere in the universe, intelligent or otherwise, will surely look at least as exotic as some of Earth's own life forms. And quite probably more so. When we assess the chances of life elsewhere in the universe, we must attempt to shake from our brains the notions that Hollywood has implanted. Not an easy task, but essential if we hope to reach a scientific rather than an emotional estimate of our chances of finding creatures with whom we may someday have a quiet conversation. The origin of life on Earth. The search for life in the universe begins with a deep question: what is life? Astrobiologists will tell you honestly that this question has no simple or generally accepted answer. Not much use to say that we'll know it when we see it. No matter what characteristic we specify to separate living from non-living matter on Earth, we can always find an example that blurs or erases this distinction. Some or all living creatures grow, move, or decay, but so too do objects that we would never call alive. Does life reproduce itself? So does fire. Does life evolve to produce new forms? So do certain crystals that grow in watery solutions. We can certainly say that you can tell some forms of life when you see them. Who could fail to see life in a salmon or an eagle? But anyone familiar with life in its diverse forms on Earth will admit that many creatures will remain entirely undetected until the luck of time and the skill of an expert reveal their living nature. Since life is short, we must press onward with a rough and ready, generally appropriate criterion for life. Here it is: life consists of sets of objects that can both reproduce and evolve. We shall not call a group of objects alive simply because they make more of themselves. To qualify as life, they must also evolve into new forms as time passes. This definition therefore eliminates the possibility that any single object can be judged to be alive. Instead, we must examine a range of objects in space and follow them through time. This definition of life may yet prove too restrictive, but for now we shall employ it. As biologists have examined the different types of life on our planet, they have discovered a general property of Earth life. The matter within every living Earth creature mainly consists of just 4 chemical elements: hydrogen, oxygen, carbon, and nitrogen. All the other elements together contribute less than 1% of the mass of any living organism. The elements beyond the big 4 include small amounts of phosphorus, which ranks as the most important, and is essential to most forms of life, together with still smaller amounts of sulfur, sodium, magnesium, chlorine, potassium, calcium, and iron. But can we conclude that this elemental property of life on Earth must likewise describe other forms of life in the cosmos? Here we can apply the Copernican Principle in full vigor. The 4 elements that form the bulk of life on Earth all appear on the short list of the universe's 6 most abundant elements. Since the other 2 elements on that list, helium and neon, almost never combine with anything else, life on Earth consists of the most abundant and chemically active ingredients in the cosmos. Of all the predictions that we can make about life on other worlds, the surest seems to be that their life will be made of elements nearly the same as those used by life on Earth. If life on our planet consisted primarily of 4 extremely rare elements in the cosmos, such as niobium, bismuth, gallium, and plutonium, we would have an excellent reason to suspect that we represent something special in the universe. Instead, the chemical composition of life on our planet inclines us toward an optimistic The composition of life on Earth fits the Copernican Principle even more than one might initially suspect. If we lived on a planet made primarily of hydrogen, oxygen, carbon, and nitrogen, then the fact that life consists primarily of these four elements would hardly surprise us. But Earth is mainly made of oxygen, iron, silicon, and magnesium, and its outermost layers are mostly oxygen, silicon, aluminum, and iron. Only one of these elements, oxygen, appears on the list of life's most abundant elements. When we look into Earth's oceans, which are almost entirely hydrogen and oxygen, it is surprising that life lists carbon and nitrogen among its most abundant elements, rather than chlorine, sodium, sulfur, calcium, or potassium, which are the most common elements dissolved in seawater. The distribution of the elements in life on Earth resembles the composition of the stars far more than that of Earth itself. As a result, life's elements are more cosmically abundant than Earth's, a good start for those who hope to find life in a host of situations. Once we have established that the raw materials for life are abundant throughout the cosmos, we may proceed to ask, how often do these raw materials, along with a site on which these materials can collect and a convenient source of energy such as a nearby star, lead to the existence of life itself? Someday, when we have made a good survey of possible sites for life in our sun's neighborhood, we shall have a statistically accurate answer to this question. In the absence of these data, we must take a roundabout path to an answer and ask, how did life begin on Earth? The origin of life on Earth remains locked in murky uncertainty. Our ignorance about life's beginning stems in large part from the fact that whatever events made inanimate matter come alive occurred billions of years ago and left no definitive traces behind. For times more than 4 billion years in the past, the fossil and geological record of Earth's history does not exist. Yet the interval in solar system history between 4.6 and 4 billion years ago, the first 600 million years after the Sun and its planets had formed, includes the era when most paleobiologists, specialists in reconstructing life that existed during long-vanished epochs, believe that life first appeared on our planet. The absence of all geological evidence from epochs more than 4 billion years ago arises from motions of Earth's crust, familiarly called continental drift but scientifically known as plate tectonics. These motions, driven by heat that wells up from Earth's interior, continually force pieces of our planet's crust to slide, collide, and ride by or over one another. Plate tectonic motions have slowly buried everything that once lay on Earth's surface. As a result, we possess few rocks older than 2 billion years, and none more than 3.8 billion years in age. This fact, together with the reasonable conclusion that the most primitive forms of life had little chance of leaving behind fossil evidence, has left our planet devoid of any reliable record of life during Earth's first 1 or 2 billion years. The oldest definite evidence we have for life on Earth takes us back only 2.7 billion years into the past, with indirect indications that life did exist more than 1 billion years before then. Most paleobiologists believe that life must have appeared on Earth at least 3 billion years ago, and quite possibly more than 4 billion years ago, within the first 600 million years after Earth formed. Their conclusion relies on a reasonable supposition about primitive organisms. At times a bit less than 3 billion years ago, significant amounts of oxygen began to appear in Earth's atmosphere. We know this from Earth's geological record independently of any fossil remains. Oxygen promotes the slow rusting of iron-rich rocks, which produces lovely red tones like those of the rocks in Arizona's Grand Canyon. Rocks from the pre-oxygen era show neither any such colors nor other telltale signs of the element's presence. The appearance of atmospheric oxygen was the greatest pollution ever to occur on Earth. Atmospheric oxygen does more than combine with iron. It also takes food from the mouths of primitive organisms by combining with all the simple molecules that could otherwise have provided nutrients for early forms of life. As a result, oxygen's appearance in Earth's atmosphere meant that all forms of life had to adapt or die, and that if life had not appeared by that time, it could never do so thereafter, because the would-be organisms would have nothing to eat, for their potential food would have rusted away. Evolutionary adaptation to this pollution worked well in many cases, as all oxygen-breathing animals can testify. Hiding from the oxygen also did the trick. To this day, every animal's stomach, including our own, harbor billions of organisms that thrive in the anoxic environment that we provide, but would die if exposed to air. What made Earth's atmosphere relatively rich in oxygen? Much of it came from tiny organisms floating in the seas, which released oxygen as part of their photosynthesis. Some oxygen would have appeared even in the absence of life, as UV from sunlight broke apart some of the H2O molecules at the ocean surfaces, releasing hydrogen and oxygen atoms into the air. Wherever a planet exposes significant amounts of liquid water to starlight, that planet's atmosphere should likewise gain oxygen, slowly but surely, over hundreds of millions or billions of years. There too, atmospheric oxygen would prevent life from originating by combining with all possible nutrients that could sustain life. Oxygen kills. Not what we usually say about this eighth element on the periodic table, but for life throughout the cosmos, this verdict appears accurate. Life must begin early in a planet's history, or else the appearance of oxygen in its atmosphere will put the kibosh on life forever. By a strange coincidence, the epoch missing from the geological record that includes the origin of life also includes the so-called era of bombardment, which covers those critical first few 100 million years after Earth had formed. All portions of Earth's surface must then have endured a continual rain of objects. During those several 100,000 millennia, infalling objects as large as the one that made the meteor crater in Arizona must have struck our planet several times in every century, with much larger objects, each several miles in diameter, colliding with Earth every few thousand years. Each one of the large impacts would have caused a local remodeling of the surface, so 100,000 impacts would have produced global changes in our planet's topography. How did these impacts affect the origin of life? Biologists tell us that they might have triggered both the appearance and the extinction of life on Earth, not once but many times. Much of the infalling material during the era of bombardment consisted of comets, which are essentially large snowballs laden with tiny rocks and dirt. Their cometary, snow, consists of both frozen water and frozen carbon dioxide, familiarly called dry ice. In addition to their snow, grit, and rocks rich in minerals and metals, the comets that bombarded Earth during its first few 100 million years contained many different types of small molecules, such as methane, ammonia, methyl alcohol, hydrogen cyanide, and formaldehyde. These molecules, along with water, carbon monoxide, and carbon dioxide, provide the raw materials for life. They all consist of hydrogen, carbon, nitrogen, and oxygen, and they all represent the first steps in building complex molecules. Cometary bombardment therefore appears to have provided Earth with some of the water for its oceans and with material from which life could begin. Life itself might have arrived in these comets, though their low temperatures, typically hundreds of degrees below 0 Fahrenheit, argue against the formation of truly complex molecules. But whether or not life arrived with the comets, the largest objects to strike during the era of bombardment might well have destroyed life that had arisen on Earth. Life might have begun, at least in its most primitive forms, in fits and starts many times over, with each new set of organisms surviving for hundreds of thousands or even millions of years, until a collision with a particularly large object wreaked such havoc on Earth that all life perished. Only to appear again, and to be destroyed again, after the passage of a similar amount of time. We can gain some confidence in the fits and starts origin of life from two well-established facts. First, life appeared on our planet sooner rather than later, during the first third of Earth's lifetime. If life could and did arise within a billion years, perhaps it could do so in far less time. The origin of life might require no more than a few million, or a few tens of millions, of years. Second, we know that collisions between large objects and Earth have, at intervals of time measured in tens of millions of years, destroyed most of the species alive on our planet. The most famous of these, the Cretaceous-Tertiary extinction 65 million years ago, killed all the non-avian dinosaurs, along with enormous numbers of other species. Even this mass extinction fell short of the most extensive one, the Permian Triassic mass extinction, that destroyed nearly 90% of all species of marine life and 70% of all terrestrial vertebrate species, 252 million years ago, leaving fungi as the dominant forms of life on land. The Cretaceous Tertiary and Permian Triassic mass extinctions arose from the collisions of Earth with objects 1 or 2 dozen miles across. Geologists have found an enormous 65-million-year-old impact crater, coincident in time with the Cretaceous Tertiary extinction, that stretches across the northern Yucatan Peninsula and the adjoining seabed. A large crater exists with the same age as the Permian Triassic extinction, discovered off the northwest coast of Australia, but this mass dying might have arisen from something in addition to a collision, perhaps from sustained volcanic eruptions. Even the single example of the Cretaceous Tertiary dinosaur extinction reminds us of the immense damage to life that the impact of a comet or asteroid can produce. During the era of bombardment, Earth must have reeled not only from this sort of impact, but also from the much more serious effects of collisions with objects 50, 100, or even 250 miles in diameter. Each of these collisions must have cleared the decks of life, either completely or so thoroughly that only a tiny percentage of living organisms managed to survive, and they must have occurred far more often than collisions with 10-mile-wide objects do now. Our present knowledge of astronomy, biology, chemistry, and geology points toward an early Earth ready to produce life, and a cosmic environment ready to eliminate it. And wherever a star and its planets have recently formed, intense bombardment by debris left over from the formation process may even now be eliminating all forms of life on those planets. More than 4 billion years ago, most of the debris from the solar system's formation either collided with a planet or moved into orbits where collisions could not occur. As a result, our cosmic neighborhood gradually changed from a region of continual bombardment to the overall calm that we enjoy today, broken only at multi-million-year intervals by collisions with objects large enough to threaten life on Earth. You can compare the ancient and ongoing threat from impacts whenever you look at the full moon. The giant lava plains that create the face of the man in the moon are the result of tremendous impacts some 4 billion years ago, as the era of bombardment ended, whereas the crater named Tycho, 55 miles across, arose from a smaller, but still highly significant impact that occurred soon after the dinosaurs disappeared from Earth. We do not know whether life already existed 4 billion years ago, having survived the early impact storm, or whether life arose on Earth only after relative tranquility began. These two alternatives include the possibility that incoming objects seeded our planet with life, either during the era of bombardment or soon afterward. If life began and died out repeatedly while chaos rained down from the skies, the processes by which life originated seem robust, so that we might reasonably expect them to have occurred again and again on other worlds similar to our own. If, on the other hand, life arose on Earth only once, either as homegrown life or as the result of cosmic seeding, its origin may have occurred here by luck. In either case, the crucial question of how life actually began on Earth, either once or many times over, has no good answer, though speculation on the subject has acquired a long and intriguing history. Great rewards lie in store for those who can resolve this mystery. From Adam's rib to Dr. Frankenstein's monster, humans have answered the question by invoking a mysterious elan vital that imbues otherwise inanimate matter with life. Scientists seek to probe more deeply, with laboratory experiments and examinations of the fossil record that attempt to establish the height of the barrier between inanimate and animate matter, and to find how nature breached this dike. Early scientific discussions about the origin of life imagined the interaction of simple molecules, concentrated in pools or tide ponds, to create more complex ones. In 1871, a dozen years after the publication of Charles Darwin's marvelous book The Origin of Species, in which he speculated that probably all of the organic beings which have ever lived on this earth have descended from some one primordial form, Darwin wrote to his friend Joseph Hooker that it is often said that all the conditions for the first production of a living organism are now present, which could ever have been present. But if we could conceive in some warm little pond, with all sorts of ammonia and phosphoric salts, light, heat, electricity, etc. present, that a protein compound was chemically formed ready to undergo still more complex changes, at the present day such matter would be instantly absorbed, which would not have been the case before living creatures were found. In other words, when Earth was ripe for life, the basic compounds necessary for metabolism might have existed in surplus, with nothing in existence to eat them. From a scientific perspective, nothing succeeds like experiments that can be compared with reality. In 1953, seeking to test Darwin's conception of the origin of life in ponds or tide pools, Stanley Miller, who was then a U.S. graduate student working at the University of Chicago with the Nobel laureate Harold Urey, performed a famous experiment that duplicated the conditions within a highly simplified and hypothetical pool of water on the early Earth. Miller and Urey partly filled a laboratory flask with water and topped the water with a gaseous mixture of water vapor, hydrogen, ammonia, and methane. They heated the flask from below, vaporizing some of the contents and driving them along a glass tube into another flask, where an electrical discharge simulated the effect of lightning. From there the mixture returned to the original flask, completing a cycle that would be repeated over and over during a few days, rather than a few thousand years. After this entirely modest time interval, Miller and Urey found the water in the lower flask to be rich in organic gunk, a compound of numerous complex molecules, including different types of sugar, as well as two of the simplest amino acids, alanine and guanine. Since protein molecules consist of 20 types of amino acids arranged into different structural forms, the Miller-Urey experiment takes us, in a remarkably brief time, a significant part of the way from the simplest molecules to the amino acid molecules that form the building blocks of living organisms. The Miller-Urey experiment also made some of the modestly complex molecules called nucleotides, which provide the key structural element for DNA, the giant molecule that carries instructions for forming new copies of an organism. Even so, a long path remains before life emerges from experimental laboratories. An enormously significant gap, so far unbridged by human experiment or invention, separates the formation of amino acids, even if our experiments produced all 20 of them, which they do not, and the creation of life. Amino acid molecules have also been found in some of the oldest and least altered meteorites, believed to have remained unchanged for nearly the entire 4.6 billion-year history of the solar system. This supports the general conclusion that natural processes can make amino acids in many different situations. A balanced view of the experimental results finds nothing totally surprising. The simpler molecules found in living organisms form quickly in many situations, but life does not. The key question still remains: how does a collection of molecules, even one primed for life to appear, ever generate life itself? Since the early Earth had not weeks but many million years in which to bring forth life, the Miller-Urey experimental results seem to support the tide pool model for life's beginnings. Today, however, most scientists who seek to explain life's origin consider the experiment to have been significantly limited by its techniques. Their shift in attitude arose not from doubting the test's results, but rather from recognizing a potential flaw in the hypotheses underlying the experiment. To understand this flaw, we must consider what modern biology has demonstrated about the oldest forms of life. Evolutionary biology now relies on careful study of the similarities and differences between living creatures in their molecules of DNA and RNA, which carry the information that tells an organism how to function and how to reproduce. Careful comparison of these relatively enormous and complex molecules has allowed biologists, among whom the great pioneer has been Carl Woese, to create an evolutionary tree of life that records the evolutionary distances between various life forms, as determined by the degrees to which these life forms have non-identical DNA and RNA. The tree of life consists of three great branches: archaea, bacteria, and eukarya, that replace the biological kingdoms formerly believed to be fundamental. The eukarya includes every organism whose individual cells have a well-defined center or nucleus that contains the genetic material governing the cell's reproduction. This characteristic makes eukarya more complex than the other two types, and indeed every form of life familiar to the non-expert belongs to this branch. We may reasonably conclude that eukarya arose later than archaea or bacteria. And because bacteria lie farther from the origin of the tree of life than the archaea do, for the simple reason that their DNA and RNA has changed more, the archaea, as their name implies, almost certainly represent the oldest forms of life. Now comes a shocker: unlike the bacteria and eukarya, the archaea consist mainly of extremophiles, organisms that love to live, and live to love, in what we now call extreme conditions, temperatures near or above the boiling point of water, high acidity, or other situations that would kill other forms of life. Modern research into the tree of life tends to suggest that life began with the extremophiles, and only later evolved into forms of life that benefit from what we call normal conditions. In that case, Darwin's warm little pond, as well as the tide pools duplicated in the Miller-Urey experiment, would evaporate into the mist of rejected hypotheses. Gone would be the relatively mild cycles of drying and wetting. Instead, those who seek to find the places where life may have begun would have to look to locales where extremely hot water, possibly laden with acids, surges from Earth. The past few decades have allowed oceanographers to discover just such places, along with the strange forms of life they support. In 1977, two oceanographers piloting a deep-sea submersible vehicle discovered the first deep-sea vents, a mile and a half beneath the calm surface of the Pacific Ocean near the Galapagos Islands. At these vents, Earth's crust behaves locally like a household cooker, generating high pressure inside a heavy-duty pot with a lockable lid and heating water beyond its ordinary boiling temperature without letting it reach an actual boil. As the lid partially lifts, the pressurized, superheated water spews out from below Earth's crust into the cold ocean basins. The superheated seawater that emerges from these vents carries dissolved minerals that quickly collect and solidify to surround the vents with giant, porous rock chimneys, hottest in their cores and coolest at the edges that make direct contact with seawater. Across this temperature gradient live countless life forms that have never seen the sun and care nothing for solar heating, though they do require the oxygen dissolved in seawater, which in turn comes from the existence of solar-driven life near the surface. These hardy bugs live on geothermal energy, which combines heat left over from Earth's formation with heat continuously produced by the radioactive decay of unstable isotopes such as aluminum-26, which lasts for millions of years, and potassium-40, which lasts for billions. Near these vents, far below the depths to which any sunlight can penetrate, the oceanographers found tube worms as long as a man, thriving amidst large colonies of bacteria and other small creatures. Instead of drawing their energy from sunlight, as plants do with photosynthesis, life near deep-sea vents relies on chemosynthesis, the production of energy by chemical reactions, which in turn depend on geothermal heating. How does this chemosynthesis occur? The hot water gushing from the deep-sea vents emerges laden with hydrogen-sulfur and hydrogen-iron compounds. Bacteria near the vents combine these molecules with the hydrogen and oxygen atoms in water molecules, and with the carbon and oxygen atoms of the carbon dioxide molecules dissolved in seawater. These reactions form larger molecules, carbohydrates, from carbon, oxygen, and hydrogen atoms. Thus the bacteria near deep-sea vents mimic the activities of their cousins far above, which likewise make carbohydrates from carbon, oxygen, and hydrogen. One set of microorganisms draws the energy to make carbohydrates from sunlight, and the other from chemical reactions at the ocean floors. Close by the deep-sea vents, other organisms consume the carbohydrate-making bacteria, profiting from their energy in the same way that animals eat plants or eat plant-eating animals. In the chemical reactions near deep-sea vents, however, more goes on than the production of carbohydrate molecules. The iron and sulfur atoms, which are not included in the carbohydrate molecule, combine to make compounds of their own, most notably crystals of iron pyrite, familiarly called fool's gold, known to the ancient Greeks as fire stone, because a good blow from another rock will strike sparks from it. Iron pyrite, the most abundant of all the sulfur-bearing minerals found on Earth, might have played a crucial role in the origin of life by encouraging the formation of carbohydrate-like molecules. This hypothesis sprang from the mind of a German patent attorney and amateur biologist, Günter Wuchtershauser, whose profession hardly excludes him from biological speculation, any more than Einstein's work as a patent attorney barred him from insights into physics. In 1994, Wuchtershauser proposed that the surfaces of iron pyrite crystals, formed naturally by combining iron and sulfur that surged from deep-sea vents early in Earth's history, would have offered natural sites where carbon-rich molecules could accumulate, acquiring new carbon atoms from the material ejected by the nearby vents. Like those who hypothesize that life began in ponds or tide pools, Wuchtershauser has no clear way to pass from the building blocks to living creatures. Nevertheless, with his emphasis on the high-temperature origin of life, he may prove to be on the right track, as he firmly believes. Referring to the highly ordered structure of iron pyrite crystals, on whose surfaces the first complex molecules for life might have formed. Wachtelschazer has confronted his critics at scientific conferences with the striking statement that, "Some say that the origin of life brings order out of chaos, but I say, order out of order out of order." Delivered with German brio, this claim acquires a certain resonance, though only time can tell how accurate it may be. So which basic model for life's origin is more likely to prove correct, tide pools at the ocean's edge, or superheated vents on the ocean floors? For now, the betting is about even. Experts on the origin of life have challenged the assertion that life's oldest forms lived at high temperatures, because current methods for placing organisms at different points along the branches of the tree of life remain the subject of debate. In addition, computer programs that trace out how many compounds of different types existed in ancient RNA molecules, the close cousins of DNA that apparently preceded DNA in life's history, suggest that the compounds favored by high temperatures appeared only after life had undergone some relatively low-temperature history. Thus the outcome of our finest research, as so often occurs in science, proves unsettling to those who seek certainty. Although we can state approximately when life began on Earth, we don't know where or how this marvelous event occurred. Paleobiologists have recently given the elusive ancestor of all Earth life the name Luca, for the last universal common ancestor. For now, naming this ancestor, a set of primitive organisms that all shared the same genes, mainly underscores the distance that we still must travel before we can pierce the veil that separates life's origin from our understanding. More than a natural curiosity as to our own beginnings hinges on the resolution of this issue. Different origins for life imply different possibilities for its origin, evolution, and survival both here and elsewhere in the cosmos. For example, Earth's ocean floors may provide the most stable ecosystem on our planet. If a jumbo asteroid slammed into Earth and rendered all surface life extinct, the oceanic extremophiles would almost certainly continue undaunted in their happy ways. They might even evolve to repopulate Earth's surface after each extinction episode. And if the Sun were mysteriously plucked from the center of the solar system and Earth drifted through space, this event would hardly merit attention in the extremophile press, as life near deep-sea vents might continue relatively undisturbed. But in 5 billion years, the Sun will become a red giant as it expands to fill the inner solar system. Meanwhile, Earth's oceans will boil away and Earth itself will partially vaporize. Now that would be news for any form of Earth life. The ubiquity of extremophiles on Earth leads us to a profound question. Could life exist deep within many of the rogue planets or planetesimals that were ejected from the solar system during its formation? Their geothermal reservoirs could last for billions of years. What about the countless planets that were forcibly ejected by every other solar system that ever formed? Could interstellar space be teeming with life, formed and evolved deep within these starless planets? Before astrophysicists recognized the importance of extremophiles, they envisioned a habitable zone surrounding each star, within which water or another substance could maintain itself as a liquid, allowing molecules to float, interact, and produce more complex molecules. Today, we must modify this concept, so that far from being a tidy region around a star that receives just the right amount of sunlight, a habitable zone can be anywhere and everywhere, maintained not by starlight heating but by localized heat sources, often generated by radioactive rocks. So the Three Bears Cottage was, perhaps, not a special place among fairy tales. Anybody's residence, even one of the Three Little Pigs, might contain a bowl of food at a temperature that is just right. What a hopeful, even prescient fairy tale this may prove to be. Life, far from being rare and precious, may be almost as common as planets themselves. All that remains is for us to go find it. Searching for life in the solar system. The possibility of life beyond Earth has created new job titles, applicable to only a few individuals, but potentially capable of sudden growth. Astrobiologists, or bioastronomers, grapple with the issues presented by life beyond Earth, whatever forms that life may take. For now, astrobiologists can only speculate about extraterrestrial life or simulate extraterrestrial conditions, to which they either expose terrestrial life forms, testing how they may survive harsh and unfamiliar situations, or subject mixtures of inanimate molecules, creating a variant on the classic Miller-Urey experiment or a gloss on Wachter-Schauser's research. This combination of speculation and experiment has led them to several generally accepted conclusions, which, to the extent that they describe the real universe, have highly significant implications. Astrobiologists now believe that the existence of life throughout the universe requires 1. A source of energy. 2. A type of atom that allows complex structures to exist. 3. A liquid solvent in which molecules can float and interact. And 4. Sufficient time for life to arise and to evolve. On this short list, requirements and present only low barriers to the origin of life. Every star in the cosmos provides a source of energy, and all but the most massive 1% of these stars last for hundreds of millions or billions of years. Our Sun, for example, has furnished Earth with a steady supply of heat and light during the past 5 billion years, and will continue to do so for another 5 billion. Furthermore, we now see that life can exist entirely without sunlight, relying on geothermal heating and chemical reactions for its energy. Geothermal energy arises in part from the radioactivity of isotopes of elements such as potassium, thorium, and uranium, whose decay occurs over time scales measured in billions of years, a time scale comparable to the lifetime of all sun-like stars. On Earth, life satisfies the requirement of a structure-building atom, with the element carbon. Carbon atoms can each bind to 1, 2, 3, or 4 other atoms, which makes them the crucial element in the structure of all the life we know. In contrast, hydrogen atoms can each bind to only one other atom, and oxygen to only 1 or 2. Because carbon atoms can bind with as many as 4 other atoms, they form the backbone for all but the simplest molecules within living organisms, such as proteins and sugars. Carbon's ability to create complex molecules has made it one of the 4 most abundant elements, together with hydrogen, oxygen, and nitrogen, in all forms of life on Earth. We have seen that although the 4 most abundant elements in Earth's crust have only one match with these 4, the universe's 6 most abundant elements include all 4 of those in Earth life, along with the inert gases helium and neon. This fact could support the hypothesis that life on Earth began in the stars, or in objects whose composition resembles those of the stars. In any case, the fact that carbon forms a relatively small fraction of Earth's surface but a large part of any living creature testifies to carbon's pivotal role in giving structure to life. Is carbon essential to life throughout the cosmos? What about the element silicon, which often appears in science fiction novels as the basic structural atom for exotic forms of life? Like carbon, silicon atoms bond with as many as 4 other atoms. But the nature of these bonds leaves silicon far less likely than carbon to provide the structural basis for complex molecules. Carbon bonds to other atoms rather weakly, so that carbon-oxygen, carbon-hydrogen, and carbon-carbon bonds, for example, break with relative ease. This allows carbon-based molecules to form new types as they collide and interact, an essential part of any life form's metabolic activity. In contrast, silicon bonds strongly to many other types of atoms, and in particular to oxygen. Earth's crust consists largely of silicate rocks made primarily of silicon and oxygen atoms, bound together with sufficient strength to last for millions of years, and therefore unavailable to participate in forming new types of molecules. The difference between the way that silicon and carbon atoms bond to other atoms argues strongly that we may expect to find most, if not all, extraterrestrial life forms built, as we are, with carbon, not silicon, backbones for their molecules. Other than carbon and silicon, only relatively exotic types of atoms, with cosmic abundances much lower than those of carbon or silicon, can bond to as many as 4 other atoms. Purely on numerical grounds, the possibility that life uses atoms such as germanium in the same way that Earth life uses carbon seems highly remote. Requirement number specifies that all forms of life need a liquid solvent in which molecules can float and interact. The word solvent emphasizes that a liquid allows this float and interact situation, in what chemists call a solution. Liquids allow relatively high concentrations of molecules but do not place tight restrictions on their motions. In contrast, solids lock atoms and molecules in place. They actually can collide and interact, but they do so far more slowly than in liquids. In gases, molecules will move even more freely than in liquids, and can collide with even less hindrance, but their collisions and interactions occur far less often than they do in liquids, because the density within a liquid typically exceeds that within a gas by a factor of 1,000 or more. Had we but whirled enough in time, as Andrew Marvell wrote, we might find life originating in gases rather than liquids. In the real cosmos, only 14 billion years old, astrobiologists do not expect to find life that began in gas. Instead, they expect all extraterrestrial life, like all life on Earth, to consist of sacs of liquid, within which complex chemical processes occur as different types of molecules collide and form new types. Must that liquid be water? We live on a watery planet whose oceans cover nearly 3/4 of the surface. This makes us unique in our solar system, and possibly a highly unusual planet anywhere in our Milky Way galaxy. Water, which consists of molecules made from 2 of the most abundant elements in the cosmos, appears at least in modest amounts in comets, in meteoroids, and in most of the Sun's planets and their moons. On the other hand, liquid water in the solar system exists only on Earth and beneath the icy surface of Jupiter's large moon Europa, whose worldwide covered ocean remains only a likelihood, not a verified reality. Could other compounds offer better chances for liquid seas or ponds, within which molecules could have found their way to life? The 3 most abundant compounds that can remain liquid within a significant range of temperatures are ammonia, ethane, and methyl alcohol. Ammonia molecules each consist of 3 hydrogen atoms and 1 nitrogen atom, ethane of 2 hydrogen atoms and 2 carbon atoms, and methyl alcohol of 4 hydrogen atoms, 1 carbon atom, and 1 oxygen atom. When we consider the possibilities for extraterrestrial life, we may reasonably consider creatures that use ammonia, ethane, or methyl alcohol in the way that Earth life employs water, as the fundamental liquid within which life presumably originated. And which supplies the medium within which molecules can float their way to glory. The Sun's 4 giant planets possess enormous amounts of ammonia, along with smaller amounts of methyl alcohol and ethane, and Saturn's large moon Titan may well have lakes of liquid ethane on its frigid surface. The choice of a particular type of molecule as life's basic liquid immediately implies another requirement for life: the substance must remain liquid. We would not expect life to originate in the Antarctic ice cap, or in clouds rich in water vapor, because we need liquids to allow abundant molecular interactions. Under atmospheric pressures like those at Earth's surface, water remains liquid between 0 and 100 degrees Celsius. All three of the alternative types of solvents remain liquid within temperature ranges that extend far below water's. Ammonia, for example, freezes at 78 degrees Celsius and vaporizes at 33 degrees. This prevents ammonia from providing a liquid solvent for life on Earth, but on a world with a temperature 75 degrees colder than ours, where water could never serve as a solvent for life, ammonia might well be the charm. Water's most significant distinguishing feature does not consist of its well-earned badge of universal solvent, about which we learned in chemistry class, nor of the wide temperature range over which water remains liquid. Water's most remarkable attribute resides in the fact that while most things, water included, shrink and become denser as they cool, water that cools below 4 degrees Celsius expands, becoming progressively less dense as the temperature falls towards zero. And then, when water freezes at 0 degrees Celsius, it turns into an even less dense substance than liquid water. Ice floats, which is very good news for fish. During the winter, as the temperature of the outside air drops below freezing, 4 degree water sinks to the bottom and stays there, because it is denser than the colder water above, while a floating layer of ice builds extremely slowly on the surface, insulating the warmer water below. Without this density inversion below 4 degrees, ponds and lakes would freeze from the bottom up, not from the top down. Whenever the outside air temperature fell below freezing, a pond's upper surface would cool and sink to the bottom as warmer water rose from below. This forced convection would rapidly drop the water's temperature to 0 degrees as the surface began to freeze. Then denser, solid ice would sink to the bottom. If the entire body of water did not freeze from the bottom upward in a single season, the accumulation of ice at the bottom would allow full freezing to occur over the course of many years. In such a world, the sport of ice fishing would yield even fewer results than it does now, because all the fish would be dead, fresh frozen. Ice anglers would find themselves on a layer of ice that was either submerged below all remaining liquid water or atop a completely frozen body of water. No longer would you need icebreakers to traverse the frozen Arctic. Either the entire Arctic Ocean would be frozen solid, or the frozen parts would all have sunk to the bottom and you could just sail your ship without incident. You could slip and slide on lakes and ponds without fear of falling through. In this altered world, ice cubes and icebergs would sink, so that in April 1912, the Titanic would have steamed safely into the port of New York City, unsinkable as advertised. On the other hand, our mid-latitude prejudice may be showing here. Most of Earth's oceans are in no danger of freezing, whether from the top down or the bottom up. If ice sank, the Arctic Ocean might become solid, and the same might happen to the Great Lakes and the Baltic Sea. This effect could have made Brazil and India greater world powers, at the expense of Europe and the United States, but life on Earth could have persisted and flourished just as well. Let us, for the time being, adopt the hypothesis that water has such significant advantages over its chief rivals, ammonia and methyl alcohol, that most, if not all, forms of extraterrestrial life must rely on the same solvent that Earth life does. Armed with this supposition, along with the general abundance of the raw materials for life, the prevalence of carbon atoms, and the long stretches of time available for life to appear and to evolve, let us take a tour of our neighbors, recasting the age-old question. Where's the life? Into the more modern one, where's the water? If you were to judge matters by the appearance of some dry and unfriendly-looking places in our solar system, you might conclude that water, while plentiful on Earth, ranks as a rare commodity elsewhere in our galaxy. But of all the molecules that can be formed with 3 atoms, water is by far the most abundant, largely because water's 2 constituents, hydrogen and oxygen, occupy positions 1 and 3 on the abundance list. This suggests that rather than asking why some objects have water, we should ask why they don't all possess large amounts of this simple molecule. How did Earth acquire its oceans of water? The Moon's near-pristine record of craters tells us that impacting objects have struck the Moon throughout its history. We may reasonably expect that Earth has likewise undergone many collisions. Indeed, Earth's larger size and stronger gravity imply that we should have been struck many more times, and by larger objects, than the Moon. So it has been, from its birth all the way to the present. After all, Earth didn't hatch from an interstellar void, springing into existence as a preformed spherical blob. Instead, our planet grew within the condensing gas cloud that formed the Sun and its other planets. In this process, Earth grew by accreting enormous numbers of small solid particles, and eventually through incessant impacts from mineral-rich asteroids and water-rich comets. How incessant? The early impact rate of comets may have been sufficiently large to have brought us the water in all our oceans. Uncertainties continue to surround this hypothesis. The water that we observed in Comet Halley has far greater amounts than Earth does of deuterium, an isotope of hydrogen that packs an extra neutron into its nucleus. If Earth's oceans arrived in comets, then those that hit Earth soon after the solar system formed must have had a chemical composition notably different from today's comets, or at least different from the class of comet from which Halley is drawn. In any case, when we add their contribution to the water vapor spewed into the atmosphere by volcanic eruptions, we have no shortage of pathways by which Earth could have acquired its supply. If you seek a waterless, airless place to visit, you need look no farther than Earth's moon. The moon's near-zero atmospheric pressure, combined with its 2-week-long days when the temperature rises to 200 degrees Fahrenheit, causes any water to evaporate swiftly. During the 2-week lunar night, the temperature can drop to 250 degrees below zero, sufficient to freeze practically anything. The Apollo astronauts who visited the moon therefore brought all the water and air that they needed for their round-trip journey. It would be odd, however, if Earth had acquired a great deal of water, while the nearby moon got almost none. One possibility, certainly true at least in part, is that water evaporated from the moon's surface much more readily than from Earth's because of the moon's lesser gravity. Another possibility suggests that lunar missions may eventually not need to import water or the assortment of products derived from it. Observations by the Clementine Lunar Orbiter, which carried an instrument to detect the neutrons produced when fast-moving interstellar particles collide with hydrogen atoms, support a long-held contention that deep frozen ice deposits may lurk beneath craters near the Moon's north and south poles. If the Moon receives an average number of impacts per year from interplanetary flotsam, then the mixture of these impactors should, from time to time, include sizable water-rich comets, like those that strike Earth. How big could these comets be? The solar system contains plenty of comets that could melt into a puddle the size of Lake Erie. While we can't expect a freshly laid lake to survive many sun-baked lunar days at temperatures of 200 degrees, any comet that happened to crash in the bottom of a deep crater near one of the Moon's poles would remain shrouded in darkness. Because deep craters near its poles are the only places on the Moon where the sun don't shine. As light-starved Arctic and Antarctic dwellers know, the sun in those regions never rises high in the sky at any time of day or any season of the year. Now imagine living at the bottom of a crater whose rim rises higher than the highest altitude that the sun ever reaches. With no air to scatter sunlight into the shadows, you would live in eternal darkness. But even in cold darkness, ice slowly evaporates. Just look at the cubes in your freezer's ice tray upon your return from a long vacation. Their sizes will be distinctly smaller than when you departed. However, if ice has been well mixed with solid particles, it can survive for thousands and millions of years at the bottom of the Moon's deep polar craters. Any outpost that we might establish on the Moon would benefit greatly from being located near this lake. Apart from the obvious advantages of having ice to melt, to filter, and then to drink, we could also profit by dissociating the water's hydrogen from its oxygen atoms. We could use the hydrogen, plus some of the oxygen, as active ingredients for rocket fuel, while keeping the rest of the oxygen for breathing. And in our spare time between space missions, we might choose to go skating. Planet from all the other planets in the solar system, notably including its highly reflective, thick, dense, carbon dioxide atmosphere, which exerts 100 times the surface pressure of Earth's atmosphere. Except for bottom-dwelling marine creatures that live at similar pressures, all forms of Earth life would be crushed to death on Venus. But Venus' most peculiar feature resides in the relatively young craters uniformly scattered over its surface. This innocuous-sounding description implies that a recent planet-wide catastrophe reset the cratering clock, and thus our ability to date a planet's surface by its buildup of craters, by wiping out the evidence of all previous impacts. A major erosive weather phenomenon such as a planet-wide flood might also have done this. But so could planet-wide geologic activity, such as lava flows, which could have turned Venus' entire surface into the American automotive dream, a totally paved planet. Whatever events reset the cratering clock must have ceased abruptly. But important questions remain, in particular about Venus water. If a planet-wide flood did occur on Venus, where has all the water gone? Did it sink below the surface? Did it evaporate into the atmosphere? Or did the flood consist of a common substance other than water? Even if no flood occurred, Venus presumably acquired about as much water as its sister planet Earth. What has happened to it? The answer seems to be that Venus lost its water by growing too hot, a result attributable to Venus' atmosphere. Although carbon dioxide molecules let visible light pass by, they trap infrared radiation with great efficiency. Sunlight can therefore penetrate Venus' atmosphere, even though atmospheric reflection reduces the amount of sunlight that reaches the surface. This sunlight heats the planet's surface, which radiates infrared, and which cannot escape. Instead, the carbon dioxide molecules trap it, as the infrared radiation heats the lower atmosphere and the surface below. Scientists call this trapping of infrared radiation the greenhouse effect, by loose analogy to their glass windows, which admit visible light but block some of the infrared. Like Venus and its atmosphere, Earth produces a greenhouse effect, essential for many forms of life, that raises our planet's temperature by about 25 degrees Fahrenheit over what we would find in the absence of an atmosphere. Most of our greenhouse effect arises from the combined effects of water and carbon dioxide molecules. Since Earth's atmosphere has only 1/10,000th as many carbon dioxide molecules as the atmosphere of Venus does, our greenhouse effect pales in comparison. Nevertheless, we continue to add more carbon dioxide by burning fossil fuels, so we steadily increase the greenhouse effect, performing an unintended global experiment to see just what deleterious effects arise from the additional trapping of heat. On Venus, the atmospheric greenhouse effect, produced entirely by carbon dioxide molecules, raises the temperature by hundreds of degrees, giving Venus surface furnace-like temperatures close to 500 degrees Celsius, the hottest in the solar system. How did Venus reach this sorry state? Scientists apply the apt term runaway greenhouse effect to describe what happened as the infrared radiation trapped by Venus' atmosphere raised the temperatures and encouraged liquid water to evaporate. The additional water in the atmosphere trapped infrared even more effectively, increasing the greenhouse effect. This in turn caused even more water to enter the atmosphere, ratcheting up the greenhouse effect still farther. Near the top of Venus' atmosphere, solar UV radiation would break the water molecules apart into hydrogen and oxygen atoms. Because of the high temperatures, the hydrogen atoms would escape, while the heavier oxygen combined with other atoms, never to form water again. With the passage of time, all the water that Venus once had on or near its surface has been essentially baked out of the atmosphere and lost to the planet forever. Similar processes occur on Earth, but at a much lower rate because we have much lower atmospheric temperatures. Our mighty oceans now comprise most of Earth's surface area, though their modest depth gives them only about 1/5000th of Earth's total mass. Even this small fraction of the total allows the oceans to weigh in at a hefty 1.